Hello again, you guys. The other day we looked at a spring mass system where you can get simple harmonic motion when you have a spring that's connected to some mass, and then you basically pull that spring so that it is either stretched or compressed from its normal length, from its equilibrium point, to some extreme, and how that weight would move back and forth, basically oscillate in simple harmonic motion. We also talked about how the energy changed. So today what I want to do is, instead of talking about a spring mass system, we're going to talk about another system that tends to create simple harmonic motion, and that's a simple pendulum. So what we're going to do here is I'm going to go ahead and first kind of compare these two systems. We're going to look at how the two systems compare at different points in their motion. And so my apologies, I scanned this out of a textbook that I had, and it kind of made a comparison between a spring mass system that you see here and a pendulum swinging back and forth. So you guys hopefully are a little bit familiar with this. They have outlined for us the equilibrium position here, okay? And then what they did is they made a comparative drawing between that spring mass and the pendulum. So for instance, notice here that the spring mass, that mass is at the equilibrium point. And so what we would say here, if you remember what we went over the other day, is that when that mass is at that equilibrium point, that essentially means the spring is neither compressed nor is it stretched, which means you're storing no elastic potential energy because it's at its normal relaxed length. All of the energy that's in this system is going to be KE. So I would say all of the energy is KE if we're talking energy. 0 PE elastic. Hopefully that makes sense to you guys. All right, I have no stored elastic. All of the energy is kinetic energy. What does that mean? Well, this should make sense to you. The velocity is at its maximum. Remember that kinetic energy is the energy of motion. And so I would expect that this is where all my energy is kinetic. That must mean that all my velocity, the maximum velocity, is going to be met in this position. This is true always. Now, if you think about this guy swinging back and forth, and what I'm going to kind of do is, on this top drawing, I'm just going to draw this pendulum when it is on the other side. And so if I think about this position where it's at the equilibrium position for the pendulum, all right, that's hanging straight down as the equilibrium position. What I would say is, as this swings back and forth, I'm going to get maximum velocity here also. You should also recognize that at this point, you have no restoring force acting here. Remember, the restoring force in the spring system is going to be the spring when it's compressed or when it's stretched. And because it's neither stretched nor compressed here, you don't have any force pushing this mass. It's moving simply because of its own inertia. And because there's no force, remember, F equals ma, that essentially if you have no force, you're not going to have an acceleration here. All right, there's no force to cause an acceleration. So according to Newton's second, if the force acting here is 0, then the acceleration acting here must be 0. Hopefully that makes sense to you. If you look at the two systems here, let me go back to this. If you think about this, all of your energy here is KE. Okay, every bit of it's KE, which means you're going to have your maximum velocity at this point, at the equilibrium point. So notice, that's a commonality between these. When you're at the equilibrium position, all of your energy is KE in these systems, and that means you're going to have your maximum velocity at that equilibrium position. However, here, if I'm at my point of maximum displacement, my spring is stretched, which means we're going to have a force that's acting. If the thing's got a displacement going this way, force is going to act in the opposite direction, pulling it back. So it's trying to pull this back. And that means you're going to have your maximum force because you have your maximum stretch here. Remember that spring force is generated by the amount of stretch that you have. So because I have maximum stretch, maximum displacement away from that equilibrium position, I got maximum force. And again, according to F equals ma, if my force is at a maximum in this position, my acceleration will be at a maximum in that position. And what I would say is that all of your energy here is PE elastic. That's all of your energy is stored as PE elastic, which means your velocity here must be 0 because you've converted all of the kinetic that you had when you were here, got converted to elastic potential when you got to here. So you've lost all your velocity and it's all turned into the stretch of the spring. Okay? Ditto here. The further I am away from that equilibrium position in the pendulum, the more, this is going to be PEG, it's gravitational potential. All of it is going to be there. At this angle, basically, gravity is pulling harder on it now than it was before. So we could say that the force of gravity, that's our restoring force, in this case, that's trying to pull it back towards the center. So I'll just say FG, it's at its max. All right, acting on this, which means I'm going to get a velocity of 0. It kind of stops right here. You could think of this as a swing, you guys, if you want to. You're going to have a velocity of 0 here, and it's pulling at its max, though. And so your acceleration as you leave that point, you're going to speed up faster during the very beginning of that movement back towards the center than you did before. Everything's reversed over here, but if you think about energy, again, your energy here is all PEG. It's all gravitational potential because you're not moving at all, and you're going to have your minimum velocity here, same as you had your minimum velocity here. Really, it's 0. That's your minimum. So you're going to have the same thing. And this just goes back and forth, you guys, between a position of maximum force, maximum acceleration, minimal velocity, to the equilibrium position where you're going to have no force acting. You're going to have an acceleration that's equal to 0 at that point because there's no force acting. And your velocity will be to maximum here. All your energy in the pendulum has been converted from gravitational potential in this position to kinetic in this. And it simply oscillates back and forth between those two positions. So, excuse me. I want to define a few terms really quickly as we move ahead. And I'm doing this on paper. This is totally an old-fashioned deal. So a couple of definitions in terms of pendulums, and I'm just going to kind of rewrite what I did on the top up there, and that is basically draw a pendulum. I didn't draw that line quite long enough, but remember that pendulum is going to oscillate back and forth between those two positions. So when you look at the pendulum, the distance from your equilibrium point to that point of maximum displacement, so there or there, that distance between those 2 points, that's called the amplitude. All right, the amplitude. So from here to there, or from here to there, not all the way, but just one way here, from equilibrium to here. Those are, that's the amplitude. Okay, amplitude. So we'll define that as the amplitude. And then we have a couple of other variables here. One is, or other factors, I would say, other ways of measuring this motion of the pendulum. So period is one, and what period is the time it takes for exactly one oscillation. So if I'm thinking about this pendulum, and you're going to see a video in a minute where I'm working with a pendulum, but basically to go from this position to this position and back, that's what the period is. Okay, from here to here and back, that's the period. Now, the frequency is your basic definition of the frequency. This is the number of oscillations that you have each second. So one way to think about this is period is the time for one oscillation. Okay, this is the time for one oscillation. On the other hand, frequency is the number of oscillations per unit of time, usually that being per second. So to get the relation per second, I don't need me on there. To get the relationship between period and frequency, it's really pretty simple. If I look at, let me get to, I already wrote something down on a piece of paper here. Oop, here it is. If you look at the units here between period and frequency, notice that they are reciprocals of each other. That when I'm measuring period, I'm measuring seconds per wave. So the number of seconds for each single wave, that's what period is. On the other hand, frequency is going to be the number of waves that you get in 1 second. But again, if you notice the units are reciprocals of each other, which basically means that period is the reciprocal of frequency. So essentially, a relationship you have between these two is that the period is going to equal 1 over the frequency. This is true always. So if I have a frequency of 200 hertz, 200 hertz, that means I'm going to have a period of 1 over 200. Okay, so essentially you're going to get, if you remember the definition of period is the seconds per wave, I'm going to get basically 1/200th of a wave from a 200 hertz frequency. Okay, you could also write this, because of the way reciprocals work, you could say that the frequency is going to equal 1 over the period. So either one of these two relationships work. If you're given a period but you need a frequency, just take the reciprocal. If you're given a frequency and you need a period, just take the reciprocal. Okay, so the next thing that I want to draw your attention to is that in order to calculate the period of a pendulum, so how long it will take a pendulum to swing back and forth. If you think about old grandfather clocks, they use pendulums to basically keep time. And what they really wanted was a pendulum that would swing to and fro every 1 second. If I could get a period of 1 second, so I get 1 second for one oscillation back and forth, then I know each time that that pendulum goes back and forth, it's going to click off a period. And if the gears and everything else that are inside of that clock can count on that back and forth rotation 1 time a second, or oscillation 1 time a second, it's going to keep good time. Each time it goes back and forth is 1 second. I know then that if I have a gear and it's got 60 teeth on it, that each minute that oscillation goes back and forth, I'm going to count off 60 seconds. So that'll basically turn that back and forth motion into rotation of the hands on the clock. That's how they developed that. Well, through experimentation, what we found is that there are certain things that cause a pendulum to change that period. Essentially, if you hang a pendulum that has a certain length right? If it has a certain length, that's the only real factor that's going to control how fast the pendulum moves. A lot of you guys may think, well, if I put a really heavy weight on the bottom, that instead of a light one, that'll make a difference. The experiment's been done. They've attempted that, trying to put heavier weights or lighter weights on it. It has nothing to do with the rate at which it moves back and forth. The formula that is accepted for the period of a pendulum is that period, capital T, is going to equal 2 pi times the square root of the length. So this is length. Oops, TH, not HT. Okay, so that's the length. And this G, you've seen this before. This is gravitational acceleration. So here on the surface of Earth, you would use 9.8 meters per second squared for this value of G. Now, the really cool thing is, and we talked about the Mars rover. If you think about this, I could determine pretty closely what the value of G on Mars would be. If all I did, if I flew to Mars and I had nothing more than a piece of string, I could tie that piece of string around a rock. I could hold that or tie that piece of string off to something that's hanging off my spacecraft or something, and then just swing that thing back and forth. If I was able to time that time it takes to go from one side to the other side and back, one oscillation, if I could time that, I will know what the period is. All I have to do then is plug in the length of the string, and I'll be able to solve for gravitational acceleration. You could do that if you want to test this 9.8 number. Put a weight on a string, tie a wrench or something to a string, and then basically support it by something, hang it, and swing it back and forth. Measure the time. If you know the time, pi, of course, is a constant, and you know the length of the string just by measuring it, you can solve and see how close you could get to our accepted 9.8 meters per second squared. So what I'm going to do here is I'm actually going to swing a couple of pendulums, one of which has a length from the ceiling. Basically, I went all the way up to the ceiling in my classroom, and I hung this down, and it's got like a croquet ball that I put on the end, and I measured the distance from here to here, and I got 2.11 meters. Okay? And then what I did is I simply swung it. And I'm going to want to measure time when I do this. But what I want to do first, you know, I forgot to load a timer right now. Okay, reset that. Oops, stopwatch is what we're looking for. So in just a minute, I have a video, and we're going to test that by looking at the time. But what I want to do first is I want to make a prediction. Based upon our formula, I want to see how close this is. So I'm going to say that my time is going to equal 2 pi times the square root of L over G. And we'll go ahead and solve for this. So this is going to be 2 times pi times the square root of 2.11 meters divided by 9.8 meters per second squared. We're going to use our accepted value and see where we come out. So that time, that period, I'm predicting then is going to be the solution that we get from this. So I am going to go back, and now not only do I need an internet timer, what do we do before the internet? I'm going to go back and get my internet calculator. You guys could use a cell phone if you want to double check me. But I'm basically going to say square root. Actually, you know what I'm going to do first? I'm going to clear that. I'm going to go 2.11 divided by 9.8. I'll use 9.81 since that's closer to the, a little more precise number, closer to the accepted acceleration. And that gives me this value that's under the radical here. The value's 0.215. And then what I'm going to do is I'm going to take the square root of that, the answer, and what I end up getting, that's once I solve just this part, is 0.4638. And now I'm going to multiply by 2, so times 2, and times pi. Darn it, this online calculator doesn't have, oh, there it is. Pi equals what I get. The answer that I get is 2.91. If we look at units here, these meters will cancel. Okay, those meters are going to cancel. And what I'm left with for a unit under the radical was essentially 1 over second squared. Or when you think about this, the denominator of the denominator becomes the unit of the numerator, which is second squared. When I take the square root, I get just seconds. So essentially what I'm predicting is that when I actually do this, I should see a time right around 2.91 seconds. Okay. What I'm going to do after that is I'm going to do this again, but I shortened up the length here so that on that second trial that I'm going to do, all right, the length of that string is going to be a little shorter. When I measured the second time, it's 1.91 meters. That's the length from the ceiling right down to the middle of that ball. And so I do a second calculation where I'm going to go 2 pi times the square root of 1.91 meters divided by 9.81 meters. And when I solve this, I'll go back over to the calculator. Let's clear that. So I'm going 1.91 divided by 9.81 equals, gives me 0.1947. Then I'm going to say square root of that answer equals, gives me 0.4412. And then I'm going to multiply by 2 again and multiply by pi. And what I get, not surprisingly, since I shortened this, the shorter the length is, according to the formula up here, I should get a shorter period of time. So the shorter the string is, the shorter this value will be. I get 2.77. Again, that's meters per second squared. So the meters cancel, and when I take the square root of that, I end up with seconds. So we get a different time. So these are our predictions right here. And what I'm going to do here in just a second is I took a video. I took a video where these, the lengths were these two values. And we're going to test it against this number. So again, I'm predicting the first time through, it's going to be 2.91 seconds. And the second time through with a shorter length, it's going to be 2.77 seconds. Okay, so I'm going to share the screen. And I'm going to take you over to where that video is. And this is me in my classroom instead of at home. Usually get me at home. So I am going to go ahead and enlarge this. and we'll play this. What I'm going to do, I better make sure that all my stuff is open and ready to go. Ooh, that's going to, you know what? I'm going to have to do that timer separate from you guys. So I'll be timing off to the side. Trust me, I'm not cheating, but I'm hoping you guys can still see the video. I'm going to use the timer over here. Okay, off screen. All right, so let me go ahead and trying to figure out if I can enlarge this and still see the timer. That's my problem. You know what? Really quick, I'm going to grab my cell phone and use that as a stopwatch. That way we can keep it big. Okay, now I have a cell phone that I can use so I can keep this big. All right, here we go. And I'm going to time it when the time is right. All right, guys, just to show you how these pendulums work, remember that the length of the pendulum is a determining factor on how long it's going to take that pendulum to go back and forth or to oscillate. So remember, that's the period, the time that it takes for the ball that I have here to go all the way to the other side and back. That's the period, one oscillation. So we're going to measure that period in a minute. And what I want you guys to realize is that I've already measured this. This is 2.11 meters from the middle of the ball all the way up to the ceiling. Okay? So that's the length of this pendulum. Now, given that length and knowing what gravity is, we should be able to determine exactly what the period for this pendulum is going to be. So we're going to test it right now. I'm going to go ahead and pull this back. And we're going to time the time that it takes to go all the way from this position to the far extreme and back. That's one oscillation. And that time will be the period. So we're going to calculate this. And then we're going to test that calculation and see if we get the same number. Right? So again, with a 2.11 meter length, here we go. I'm going to let it go a couple of times, and then we'll just divide our number in two to get a number. Here we go. Okay. So we're going to go ahead and... Okay, I'm going to pause it right there. The number that I got measuring that time for 2 oscillations was 5.72. If I divide that in 2, since what we really saw here was 2 oscillations, I'm going to get, I'm doing this longhand division. The value that I get per oscillation was 2.86 seconds. Now, what we predicted was 2.91 seconds. So basically, I'm off by 0.05 seconds. That's not too bad of an error. I mean, I'm basically off by, in roughly 3 seconds, I'm off by 0.05. So that's about 1/60th of the total value. That's less than 2% error. Let's put it that way. So it's about 1.5%. Pretty close. Okay, first time, and we're going to test it against the predicted time. Now, if length really does control the period of time that it's going to take this pendulum. So here you guys can see I'm shortening this length to test the idea that a shorter length should give us a shorter period, a faster period. So now this thing's hanging a little bit higher. I'm going to measure it from the ceiling. So here I've got 1 meter. And to get to the middle of the ball, it's about 1.91. New length is going to be 1.91 meters. And we're going to do this again. And theoretically, because our length is shorter, we went from 2.11 to 1.91. Theoretically, what we should see here is a more rapid period. It's going to take less time to go all the way over and back. All right, so what we predicted here when I calculated that number before was that we would see a period of 2.77 seconds. Okay, so let's see how close we were. So here we go, we're going to do it 2 times again. And see how it matches up with the predicted. Here we go. Oh, darn it. I got to go back a little bit. From 2.11 to 1.91. My phone went to snooze mode, and when I pushed it, it didn't start. Rapid period. It's going to take less time to go all the way over and back. So here we go. We're going to do it 2 times again. Okay. And see how it matches up with the predicted. Here we go. So we take our total time. Okay, so what I got when I did this was I got a value of 5.40. If I divide that in 2, since we watched 2 oscillations, not just 1, so we have to divide that time in 2 to get the period. I get, again, doing long division, 1, 4, that would be 7, 0. All right, I was off a little bit more on this one. But the time that I got, the period that I got was 2.70. So maybe I was just a little bit quick on the start and stop maybe. But what we predicted was 2.77. So we were again off by 0.07 seconds, still less than 1/10 of a second off of what we predicted. Okay, so this formula really holds. It works well, you guys. To predict the motion of a pendulum. And really, like any mathematical formula, you can use it to solve. I could use it to solve for gravity. I could use it to solve for length. If I know the other variables, I mean, that's how math works. So to show you an example of the kind of stuff you're going to see, we're going to look at this question that's right here. And not really difficult, but it's pretty useful if you're dealing with anything that's a pendulum. This would also, you could basically time how or predict how long a kid is going to take to oscillate back and forth on a swing. As long as you know the length of that swing, you can make that prediction and you're going to be pretty close. You need to know the height of a tower, but darkness obscures the ceiling. Oh no. You note that a pendulum extending from the ceiling almost touches the floor. How fortunate, really. And that the period is 12 seconds. And so I know that the period of this oscillation is 12 seconds. Okay? Could I figure out frequency if I know this? Pretty easy. You're just going to take the reciprocal of it, right? If you know t, the frequency is always going to be the reciprocal of t. So it wants to know how tall the tower is. And so what they're looking for really is, what's the length of that pendulum that extends from the ceiling to the floor? Okay, so I know my formula. T equals 2 pi times the square root of L over G. Remember, one mistake I see people make, they don't put the G under the radical. The L and the G are both under the radical symbol. So if I want to solve for L, how am I going to isolate this? How am I going to isolate L? Well, the first thing I would do is I'm going to get rid of the 2 pi on this side by dividing both sides by 2 pi. That's going to cancel those two out, leaving me the square root of L over G on the right-hand side and t over 2 pi on the left-hand side. Square both sides now. We want to get rid of the radical. So that's going to leave me L over G equals T squared over 2 pi squared. Okay. Now just multiply both sides by G. And so my end formula would essentially be L equals T squared times G over 2 pi squared. And if I start plugging in some numbers, T's 12 seconds. We're going to square that. G is 9.8 meters per second squared over 2 times 3.1416, da 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 da. You guys know what pi is. And actually, you know what I'm going to do is wrap both of those and then square that. So in the numerator, let's get the calculator loaded up here again. I don't want the timer. I want, why did that go away? Anyways, let me get calculator. So I'm going to say 12 squared. So 12 times 12. Times 9.8. I'll use 9.81. Gives me 1412.64. Then I'm going to divide that by 2 twice, basically to square it. And then divide by pi twice. And what I end up getting is 35.78, or I'll call this, really I should call it 36. But if I look at units here, you guys, I've got seconds squared here. They're going to cancel out those seconds squared, and I'm left with meters as a unit, which means my algebra was probably right, because for length, meters makes total sense. Okay, so the height of this building should be right around 35.8. I'm suspecting when I check it right now, they are going to say it was 36. This inner text, that was a sample problem. They said 36 meters. Okay, which makes sense. You got to round to 2 sig figs, not 3, because the time that you had was 12 seconds. So I would round this to 36 meters, and that would be the height of my building. Pretty simple equation to work with. Just be careful on your algebra. So I'm going to go ahead and post a problem set for you guys, and you guys can get to work on that. In terms of period of a pendulum, we're done. So I will see you guys later. Let me know if you guys have troubles with any of the homework on this, okay? Catch you later, guys. Bye-bye.